Hey, math people. This is lecture 4 of the second chapter of differential calculus, which is calculus 1. You can go around and click through the timestamps to see what you need. The video is going to look like this. We're going to do some graphical matching of derivatives, and we're going to go into higher derivative graphical matching. We'll look at different notations and then finally do some work with higher derivatives. And take a lot of second derivatives, so derivative of derivatives, which is a fun idea, and then just do some other fun calculus stuff in case you need it. Okay, so a little warm up. Write the expression that represents the derivative of just y for each of these three scenarios. See if you remember Lagrange, Leibniz, and Newtonian notation 3, 2, 1. Here they are. So y prime is the derivative expression in Lagrange. That's a notation we're going to use mostly. And then Leibniz, dy dx. Newtonian has got that little dot up top. Okay, that's it for now. But I want to start maybe talking about this idea of higher order derivatives. Okay, so if we have a derivative, which is just some function, so 8x minus 2, you can take the derivative of that and you can just keep going. So I want to build up to that graphically first. We're going to do some matching. So match the functions 1 through 4 with the numbers a through d. So see how you do here? This is just a way of building that intuition, that graphical kind of visual intuition behind functions and their derivatives. So 3, 2, 1. Okay, so looking at we can just start from the first graph. We see here that we have a negative slope all the way up to 1, and then we have a positive slope thereafter. So I would be looking for the choice that has a negative to positive output. So negative outputs when we're to the left of 1, positive outputs, positive slope in the graph when we're to the right of 1. That choice is right here. You can see here all of the outputs are negative on the left of 1, all the outputs are positive to the right. Next one, we want to choose a graph that goes below, above, below, because my graph goes negative slope, positive slope, negative slope. So below, above, below. And the choice that does that would be choice D here, so that it goes below, above, below the x-axis. Okay, looking at 3, we just go negative slope to positive slope to negative slope. So that's going to match over here. That's below, above, below. And then 4, it's actually a positive slope the whole time. It just goes to like a 0 slope, like for like a moment when x is equal to 0, right? Positive, 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 and then 0, and then positive thereafter. So that's going to be choice 4 here. Always, now, if you're confused, you're like, wait a minute, isn't that a negative slope? These are outputs, right? So if we're looking about the slope of blue, we want the outputs, so the derivative here within orange to be positive. Positive slope, positive outputs. So we got positive outputs through and through, except for at 0. It's like a slope of 0. And hopefully you're kind of with me here with this notion that, you know, the slope is more intense here. It's more positive, and then it gets closer to 0. Then it's close to 0, and then it's bigger. So bigger, close to 0, 0, close to 0, bigger. All right, so like do it again. Do it again. So I want now to match the derivatives a through d with their derivatives, and I guess I'm just calling it I through IV, which is Roman numerals. Yeah, so go ahead, do that. See if you can do the matching one more time. 3, 2, 1. So you should be getting this idea, is that if we are looking at now orange, and I want to find the slope of orange, it's positive for the first half and negative for the second. So I want positive outputs and then negative outputs. Now I actually have 2 of those that match that, right? Positive and then negative. But I encourage you to kind of look at the fact that, you know, this appears to look like cosine or like a trig function. You can see it kind of leveling off here. It doesn't just keep going like a parabola would. You know, it kind of starts to taper back into a slope of 0. So just, you know, I guess soft keep that in mind as we kind of hit the rest of these up. So as of right now, I would be like A matches with either 2 or 3. And then if I look at B, it's a negative slope to positive slope. So that one only matches with the first one right here. Negative output, positive output. Okay, looking at C, this is just a constant slope of whatever this is, 2. So I just want a constant of 2 so that these graphs match. And then lastly, if I want to match D here, I want a positive and then negative. Okay, so, but this is a parabola and it's just going to keep going. You can tell, look how intense that slope eventually gets over here. So this would be the one that matches. So you can see our positive slope to negative slope. That's the same as positive slope to negative slope. But here we start to level off a bit. So A is going to match with 3, and then this I, and then D is going to match with I. 2 I's, like me. Okay. So what did we do here? What we just did was we came up with the second derivatives. You can just keep going. That's all the real takeaway is. It's good graphical practice, build that intuition, but taking a further step back to what the main objective is, we just found f double prime. We just found the second derivatives of blue. So the first derivative of blue is orange, and then the second derivative of blue is purple. So the nth derivative, you can keep going. I said f double prime. That's what it's going to look like in Lagrange notation. We just put in 2 apostrophes and then 3. And then eventually it gets too many, and then we just start putting the number 4 or 5 or 6 in parentheses as like a power of f. So that's Lagrange notation. Leibniz is a little interesting. Leibniz, you can kind of think about it this way. If we were to take the derivative of y, so take the derivative as d dx, you would get dy dx. So if you were to take the derivative of taking the derivative of y, you have the d dx of the d dx of y. So you have 2 d's and you have 2 dx's, so just kind of like square them. Now here's the thing, that's not actually what's happening. You're not just like squaring them. This is like a notational thing. This is just what we choose for the methodology of communicating this in written language. But this expression means second derivative. This expression means third derivative. This expression means fourth derivative in Leibniz. And then for Newtonian, don't worry about it. You just put more dots on top, and it's hard to see. So we don't do it. All right, so practice taking higher order derivatives. What I want you to do is practice writing this in Lagrange and then Leibniz notation. And then just keep taking derivatives. Take the first derivative and then take the derivative of the derivative, the rate of change. And then take the derivative of the derivative of the derivative, which is rate of change. And it starts to get wacky. See if you can do this. 3, 2, 1. The process is not that bad, right? You're just doing product rule over and over and over again. Or not product. The other one, power, starts with the P. So, you just keep on putting more primes in play if it's Lagrange notation. And if it's Leibniz, we like raise that D to that next power and raise that DX to that next power, but it's not powers. It's like a notation. All right, and if you just keep doing this, by the way, like notice how this terminated to 0. This is true for all polynomials. If you just eventually, there we go. If you just keep taking derivatives for all polynomials, you can kill them all. So if you just don't like algebra, you want to destroy any derivative in sight, just take the n plus 1th derivative and it'll go to 0. We took the 5th derivative here and it went to 0 for a 4th power. 4 plus 1 is 5. All right, so take the second derivative of each of these. Remember, write these as x to the 1/2 and then x to the negative first, and then take your derivatives. So I'll give you some time. 3, 2, 1. Here you go. First derivative looks like this, and then you just do it again. You just do it again. You can rewrite them as powers like this, right? You can bring it back to the denominator, and then take that radical 2, that index of 2, and use it as a square root there if you want. You can also leave it this way. And same story with 2. 2 is a little bit lighter though, right? You're just bringing that x to the negative third down below. All right, we have like a product rule looking case and a quotient rule looking case. The world's your oyster. If you want to multiply this out and just use power, feel free. If you want to use quotient rule, feel free. I mean, you can actually even bring this 2x squared up top and then use product rule if you wanted to, although you need chain rule in that case. You have some options. See how it goes. 3, 2, 1. So I guess I just did product rule, and I simplified it out, and I got this expression, 6x squared minus 6x plus 2. After that, I just did power rule. Done. Over here, I just didn't want to do So I did the opposite over here. I skipped quotient rule because I hate quotient rule. Low, D, high, minus. It's got a fun noise to it. Low, D, high, minus high, D, low, all over low squared. But I don't know. There's just too much stuff going on. I just divided each term here by 2x squared. Went ahead and did algebraic simplification. And then here's a nice constant. So that went away and just power. And then I did power rule again for the y prime to y double prime. So here's my final answered expression. All right, we're gonna end it with just some other derivative stuff here. I'll show you how to do derivatives in Desmos as well. I just didn't know where to squeeze some of these mini lessons in. So if you have some mess, some just nightmare, something you're just not looking forward to taking the derivative of, we have an option for you, and it's called a calculator. What's the point of any of this if I have access to my calculator, right? So look, I like to do this one, okay? If f of x is, we'll just say x to the third, if I want to know the slope at 1, there it is. I want to know the slope at that value. What I could do is I can do derivative, right, and get 3x squared, and then plug in 1, and then 3 times 1 squared is 3. Or I can do this, f prime. So this is on Desmos. This is the calculator that I use in my class. I just said, you take the derivative of this and you plug in 1, you get 3. Well, check this out. When you plug in 1, you get 3. So see if you can practice doing, literally just that on Desmos for, I guess, each of these. You can also do this one mentally, like x squared, the derivative of x squared is blah. And if you plug in 5, you should get blah. So see if you can test that on your own. 3, 2, 1. Right. All right. So if you were to do that same process, you would get 2.478. On the AP exam, if you're taking this as an AP class, you only need to round to 3 decimal places. So that's what I did here, probably, I'm going to guess. If you're using a TI-84, it's math 8, and then you would plug it in like this. You would put an x here, whatever your function is here, and then what you're trying to evaluate it at here. If you're using one of those calculators. But if you're using Desmos with me, we can just do, okay, well, f is x squared, so f prime of 5 is 10. So the derivative of x squared is 2x. Plug in your 5, you get 10. 2 times 5 is 10. And then for the last case, what if you're given a table and you're not given a function instead? If I wanted to find f prime of 5 and I only have the snapshot of what is happening at 4 and what is happening at 6, I can't just read between the lines here and just say, oh, it's got to be something like the average in between. We don't know that, right? What's the average of 20 and 32? Hello? 20. Don't judge. Oh, 26. Yeah, that makes sense. 12 in between, so 6. Okay, can I just assume that at 5, my output is 26? Absolutely not, right? Because look at the way that this pattern is behaving. We go 4, 8. Okay, maybe it's linear. 8 to 20, it's already not linear. It blows up here by 10. So you cannot assume that these things are lines. What you have to do is approximation technique. Think about how the tangent line was instantaneous rate of change at a point. The secant line is kind of like change between 2 points, right? That's what we're going to do here. We're going to be finding the slope of the secant line from 4 to 6, which is average rate of change. You just do average rate of change here. Just do change in y over change in x. So 32 minus 20 all over 2. The slope is probably like 6. You can approximate it to be 6, but it's not exactly 6. We don't know what happens in between. Yeah, and you can only do this for when the function's continuous too, differentiable. Okay, that's it. Math on.